Today we'll be using equipment made from only the finest hardware store parts to invent cutting-edge, self-cooling fabric in my backyard workshop. Hi, I'm Ben. Thanks for being here. In previous videos, we've developed radiative sky cooling coatings, which can keep a surface several degrees below air temperature, even in direct sunlight. More recently, I've turned my attention toward the development of fabric, which could achieve those same cooling effects. Where paint might be effective in some circumstances, like cooling a building by painting the roof, or by cooling air that flows through sky-facing panels, it's limited in application to these sort of stationary, rigid surfaces. A fabric, on the other hand, is flexible. It could be made into a sheet that can be thrown over anything for temporary cooling, or made directly into clothing that keeps you cool all day long. In my previous video in this radiative cooling series, we ended with the discovery of a successful, although very tedious method for making small quantities of fibers from a common 3D printing plastic, PLA, which achieved a very strong cooling effect in sunlight. It took about a half hour to make this cotton ball-sized lump of coarse, brittle fibers, dragging them out by hand with a homemade metal rake thing from a container of gooey polymer soup. This process leaves a lot to be desired in terms of efficiency, and the fibers themselves are not even close to the consistency required to make a soft, flexible fabric. This is a proof of concept in its most primitive form. It proves that PLA fibers can be made to have radiative cooling properties, and that's pretty much all it does. With the possibility of a cooling effect confirmed, the task now is to actually learn how to turn this material into proper fibers with reasonable strength, flexibility, and other attributes necessary for making a genuinely useful fabric. In my first fiber experiments, I was attempting to melt PLA in a cotton candy machine and just spin the fibers out like the machine is made to do. This didn't end up working, at least not how I was trying to do it, but I think the concept is still a good one. Many comments suggested various ways that fake spiderwebs are created from either hot glue or rubber cement, basically spinning a container of the mixture in front of a fan with tiny holes for the liquid to shoot out into the air as threads. That's basically how a cotton candy machine works, but with extra airflow and simplified to its bare components. This seemed like a good place to start. I purchased this inline ventilation fan with an attached speed controller, which I thought would give me a useful variable to play with. The only modifications required to turn this into a fiber blower were to attach a small container to the front of the fan, and I also flipped the internal motor bracket around so that the fan blades and container would stick out past the front edge of the housing, making room for the threads to fly out without hitting the inside walls. I of course can't melt plastic in this setup using heat, so the PLA is dissolved using a solvent of ethyl acetate, in the same mixture I originally drew out into fibers using my metal rake. The PLA is made extra stringy by adding a small amount of another long-chain polymer into the solution called PEO, polyethylene oxide. This is like molecular spaghetti, super stringy, and it causes the whole solution to turn into flubber. For my first test with the fan, I had some of my fiber making solution still saved from previous experiments, and I piped it into the attached container, which has two small pinholes at the front to hopefully eject fibers. To collect them, the idea was to try using a window screen. I recently watched a few videos about making paper where a screen is dipped into water containing wood pulp. The screen collects the cellulose fibers in an even layer, and then the whole sheet just peels off. Seems like as good a method as any for trying to catch the fibers in this process. So I turned on the fan. This was a huge success. I almost immediately noticed fibers collecting. They're very thin, so it took a while to start building up a significant layer. Meanwhile, the only way to refill the container on the fan was to power it down, unscrew it, and pipe in another few milliliters every 2 or 3 minutes. I probably had to do this 10 times to get through my little beaker of liquid. The pinholes occasionally clogged also, so I had to stop the fan again every so often to repoke the holes. One thing I was trying to figure out as this went on for quite some time was how far away the window screen should be. As the fibers are blowing through the air, the solvent which makes the plastic liquid is evaporating. If the screen is too close, the fibers might still be fully liquid when they blow into it, basically ending up like a coat of permanently attached spray paint. If the screen is too far away, some of the fibers might not actually land on it, and I was realizing that I kind of wanted them to not be fully dry by the time they collect, because if they're still a little bit sticky, they might bond together, and the result would be more than just a mat of loose fibers, but an actual fully formed piece of fabric. I don't know that I ever figured out the ideal screen distance during this test, but fortunately it turned out to be a pretty forgiving process. My first batch of fibers peeled off in one piece. How awesome is that? Hey, why are you shouting? Why are you being so noisy when I'm trying to work? My sponsor for this video is Delete Me. There are literally thousands of data brokers who make money by scrounging the internet, compiling public and government records of personal information like my address, phone number, email, and who I'm related to, and packaging that into a product that they will sell to anyone, like telemarketers and scammers. Now, you could Google yourself, try to find each of these data brokers that are selling your information, and manually fill out the required forms to have your data removed, and they legally have to do so. But there's nothing stopping them from opening a new website, so you have to submit another takedown, over and over and over again. Delete Me regularly scans the internet for you and submits takedowns for your personal information whenever it appears. This list is just some of the sites that they submitted takedowns for on my behalf in the first few weeks that I used them. If you'd like to make it a lot harder on telemarketers, scammers, and identity thieves to get your information and that of those you care about, check out Delete Me. You can get a 20% discount on a US consumer plan by using my link, joindeleteme.com/Nighthawk, and using the code Nighthawk on checkout. This is basically what's called a non-woven fabric. It's about the same texture and pretty similar in strength to a coffee filter. This can definitely be improved, but for a first test, this is about the best result I've ever had. I took right to making a community post on YouTube to show this off, took a few quick measurements with my thermal camera, and then had to leave town the next day for about a week and a half, right when it was getting exciting. But that's okay, the same process was bound to work just as well once I returned home. Right? While I was away, the weather had gotten much colder, and this seemed to cause all sorts of issues. First of all, my plastic solution freezes right around room temperature. So the colder the weather is, the faster I have to work to keep the liquid from freezing in its container. It also seemed much too gooey all of a sudden. Instead of forming fibers, it formed thick strands of snot. I did another quick test using a jet from an air compressor to try to blast this mix into a web of fibers, but still that did not work. I decided the fan method had worked once, at least in warmer weather, so I should stick with the same basic process, but with a few improvements that should make it easier to repeat the conditions of my first success. Time to build a new machine. This is my new creation. We built this over the course of several live streams on Patreon, and I say we because this definitely ended up being a collaboration with everyone who watched it live and gave me real-time feedback on my design options. This is a better machine thanks to my Patreon supporters. Just one more thing for me to be overwhelmingly grateful to my patrons for. Thank you. So the basic concept is this. Considering that the colder weather is what I believe to have caused most of my issues using the old machine, this new one has a hot air input. This way, no matter how cold the weather, I can keep my plastic mix warm until it flies out of the spinning head. Hot air is supplied by a hairdryer blowing through a central tube, and once the fibers fly out of the container, the heat is no longer as important. So I use a room temperature flow of air in this outer sleeve to blast them forward, provided by a 6-inch inline ventilation fan at the back of this elbow. The other issue with the basic fan setup is that I had to shut it down every few minutes to refill, and that's not going to work if I want to make anything larger than a tiny patch of fabric. I need an option for continuous injection without shutting down the machine. The only way I can think to do that is from the back, because anything in front of the spinning head would intercept the fibers in midair. So, the shaft that this container is mounted to is hollow. The shaft extends back through the middle of the central tube, which keeps it warm with air from the hairdryer. And then it's connected by a pulley to this variable speed drill so that I can control how fast the shaft spins. That controls the speed of the spinning head, which is probably an important factor for fiber production, although I'm not exactly sure of all the effects a change in speed may have. In any case, while the original design had the container directly coupled to the fan, in this design, I can adjust it independently. But concerning the need for a continuous method of supplying fresh plastic solution, we now have the hollow shaft, which can be used to inject the plastic. But this also needs to spin freely. And I would prefer that the hopper, or whatever we use to inject plastic, does not need to spin along with it. To connect a spinning tube to a non-rotating one, there's a type of fitting called a swivel connector. And they are not cheap. Not wanting to spend several $100s on a part that I wasn't even sure would be resistant to the chemicals I'd like to push through this, I came up with a DIY option that is so good, it almost deserves its own video. Except it's so simple it would only be about 30 seconds long. It's a little piece of Teflon tube. This is a tube sold as a part for 3D printers, 8 millimeters in outer diameter, which is the same as the inner diameter of this spinning shaft. Teflon is self-lubricating and extremely chemical resistant. So if I stick the end in here, it should still slip easily enough that the shaft can rotate. Actually, the Teflon was a little bit oversized, so at first it took some effort to force it into the shaft. But after a few minutes of running the machine, the friction causes heat, which made the Teflon shrink to a perfect airtight fit. It works super well with no leaks. To prevent this little tube from whipping around with the shaft, I insert it into a steel sleeve with a bend in it. The bend keeps the Teflon from rotating, and the steel tube can be easily clamped to a stationary support. After running the machine, the tube and shaft, of course, needs to be cleaned out, and that's super simple to do by just retracting the Teflon and then pushing a piece of paper towel through it with a wire. Good as new. I'm sure a million people have thought of this rotating connection before, but it was a new idea for me, and I'm real happy with it. We now have a cheap way to continuously feed new plastic into the machine without slowing down. It was a fairly critical design goal for this to have good chemical resistance to a wide variety of stuff, because I want the option to experiment with all sorts of different materials for making fibers. I am currently focusing on PLA, and there's good reasons for that. First of all, it just so happens to have a really good infrared emission spectrum for radiative sky cooling. There's something called the atmospheric infrared window, which describes a range of infrared light that does not interact with Earth's atmosphere. And that's the range we're aiming for in a good sky cooling material. And if we overlay PLA's emission spectrum on this graph, a big chunk of it falls right in the window. For my previous cooling materials, I've had to specifically search out various pigments, which have this sort of favorable emission spectra. But in the case of PLA, it's just naturally good at this. It also helps that it's a bioplastic that can be made by fermenting natural starches and sugars into lactic acid, and then it can also naturally break down again. Now, I know it's very popular to point out that PLA's ability to biodegrade is overblown, but I also think the correction is overblown. It does biodegrade eventually in most circumstances, and you can look up some articles about all the ways being developed to make bioplastics more easily compostable. You'll find that some of them have already made it into real-world products. It's really not that difficult of a problem, especially when compared to other plastics that are probably on all of our bodies right now. PLA also breaks down from UV exposure in sunlight, which does complicate its use as an outdoor fabric. But I think that will be easy to solve with various coatings. But one step at a time. If PLA doesn't turn out to be the perfect choice, the things we learn in trying it will equip us to more easily switch to other materials in the future. So after building this, surely we'll finally have the beautiful fibers I've been looking for. We fired it up for the first time during the live stream and ended up with more rubbery snot. The same problem I had started having in the simple design, even now with the addition of heat. In fact, the heat caused other problems, causing the solvent to boil in the injection tube, forcing liquid out of the top like a volcano. Being gentle with the heat is apparently important. Now, the recipe I had been using never changed from my first successful result, but clearly something is different for it to suddenly be super thick and unable to make threads. While building the new machine, I used the old one a few more times, and every so often got a pretty good result. It was really inconsistent, and I started to suspect that the weather may not be the only problem. The cold was definitely causing some issues, with the plastic freezing, which the warm input on the new machine did fix. But the thick rubbery goop was still not forming threads. It must be an issue with the plastic recipe itself, but since the formula hadn't changed, the only other thing that could be different is age. The first time I had success, I used a mixture that was a few days old, and that is really all I needed to learn what had been going wrong here. So remember the molecular spaghetti additive I've been using called PEO? This is an extremely large molecule in a chain-like form called a polymer, and the longer the chains are, the gooier the mixture is. The chains break fairly easily, especially when mixed with other chemicals like the solvent that I'm using to dissolve my plastic. The longer the PEO sits in that solvent, the shorter the molecular chains get, making the mixture less gooey. Now, the PEO that I've been using is about the largest chain size that I could find, with a molecular weight between 8 and 11 million grams per mole. That is a huge molecule. Now, I could use this in my mixture still and just let it sit for a few days to break down, or I could try switching in a shorter chain length PEO powder and see if it works to make fibers right away. This is about 1 million grams per mole, and so it should be significantly less gooey, while hopefully still giving me the benefits needed for strong fibers. Thankfully, this did indeed give me my first success with the new machine. Notice that the collector is different now. The first fabric that I made on the old machine easily tore in circular arcs around its center, because the threads were all facing the same direction. This time the screen rotates so that the circular pattern that the fibers make when coming out of the spinning head overlap one another like a spirograph, making the fabric strong in all directions. This should also allow me to make larger pieces of fabric because I can cover more of the screen as different parts continuously rotate in front of the blower. Another option for large pieces of fabric might be to collect it on something like the belt of a treadmill, but I think this works well enough for now. I'm curious if you have ideas for collecting these fibers in larger sheets. One thing going for this method is that peeling the fabric off a screen is incredibly satisfying. From this point, I played around with my plastic recipe a little bit to maximize brightness, because of course we're trying to reflect all the sunlight that we can so that the cooling effect is amplified. This is by no means the best possible recipe for radiative cooling fibers, but it is a pretty good starting point for being invented by some guy in a barn. The recipe is as follows. 100 milliliters of ethyl acetate is used to dissolve 8 grams of PLA with stirring and gentle heat, about 60 degrees Celsius. Once dissolved, add 8 milliliters of 91% isopropyl alcohol, and then 0.08 grams, a very tiny amount, of 1 million molecular weight polyethylene oxide. This is the finished fiber solution. A few changes have been made since my last video. For one, I'm now using much less PEO in favor of more alcohol in the solution as the main contributor to make the plastic reflective. The mixture of solvents causes nanovoids in the fibers, which scatter light. I'm now also using PLA pellets instead of chopped up filament, and the main reason for doing this is not because of price or convenience. It's because I know that these are pure PLA. 3D printing filaments may have other mystery stuff thrown into the plastic to change how it prints, and I don't need more mystery added to this already difficult process. These pellets are PLA type 4043D. I don't know if this type is better or worse than others, but I at least know exactly what these are. This recipe works really well to consistently make super fine, bright white fibers, and they're surprisingly flexible and strong. The only question now is how well does this fabric actually work for radiative cooling? Here's a sample in my test box being compared to ordinary white paint and a sample of previously successful homemade cooling paint. All of the samples in this box are in direct sunlight. It appears that the fabric is now outperforming even my best cooling paint. Next to a sample of ordinary white cotton, it also stands out as much colder. Now, the emissivity of PLA is slightly different than the other samples in this box, so we need to confirm the readings by more accurate measurements. But this is a promising first result. Previously, all of my paints and coatings required a protective film over the top in order to reach temperatures colder than the surrounding air. The film protects the surface so that the cooling effect doesn't have to fight against a warm breeze constantly blowing over it. In the case of my fabric, this is the first radiative cooling material I've made that seems to stay below air temperature even without a protective film, and even in direct sunlight. That's amazing. I have not yet put a lot of effort into perfecting this recipe. It's just the first version that seems effective so far and is easily turned into a fabric using my machine. It does look promising, but remember, the results that follow are based only on this first version, which almost certainly could be made much more effective. With these initial results in hand, I think it's time we put this fabric to a more practical test. Let's try applying it to a hat, and maybe create my first piece of clothing that can cool a person down in real-world working conditions. The first step here was to make several large batches of fabric so that I would have plenty to work with. I then traced out and cut several pieces to fit over the brim of my hat, starting with a double layer because I'm assuming I'll need extra thickness to block out all light. Any that passes through the fabric might be absorbed by the hat underneath. And here it is. As a start, I only covered the brim so that we could compare the covered sections to the normal hat material and hopefully notice a strong difference in temperature between them. If the results look good, I'll cover the rest of the hat. The first reading looks consistent with our early tests. The outer surface of the brim seems very cold, but it doesn't look quite so good when we move around to the side and see that the second layer of fabric and the hat itself is still getting warmed by the sun. Heat seems to be retained by the lower layers. By the way, this second layer of fabric reading as a high temperature proves that it's not just a material calibration error making the outer surface appear cold. These layers are definitely different temperatures, the top one being much colder. I think I know what's happening here, and I don't know if it has a name besides the polar bear effect. Polar bears have light-colored fur, which reflects a lot of sunlight, but they can still warm up in the sun because their skin is dark, and whatever light makes it through the fur bounces around until it's inevitably absorbed by the darker skin as heat. Even though the outer surface of my fabric is extremely reflective, it's not a solid layer and fails to block 100% of light. Whatever fraction of light doesn't bounce off the outer surface is bounced around in the lower layers and eventually retained as heat, probably after contacting the darker colored hat. An extra problem is that even though the outermost surface is cold, there's not enough contact, not enough thermal conduction to transfer heat between layers. This is the same problem with using ordinary styrofoam as a radiative cooling material. Many people noticed in my earlier project that my styrofoam box, which houses my cooling samples, seems colder than the samples themselves on the thermal camera. And that's not an illusion. The surface of a white styrofoam sheet can get very cold through sky cooling effects, and it absorbs very little sunlight due to its highly reflective, porous nature. However, the reason the surface gets so cold is because it self-insulates. There's very little heat that travels through it, and so the surface doesn't have to fight against heat creeping in through the back. And that makes the cooling effect look very strong, but it's literally only skin deep. As a test to increase the thermal conductivity of my cooling fabric, I decided to try cutting a piece of foil to fit over half of my hat brim. I then used this to back a single layer of fabric, holding it down with spray adhesive. My hope for this is that the fabric will have better conductivity being physically cemented to the foil, which will also act as a reflective surface to reject extra light that passes through the first layer. The other half of the hat will get a third layer of fabric to see if simply increasing the thickness improves the original result. This did indeed make things interesting. The thermal reading from the front of the hat shows the triple layered side as much colder than the single layer backed by foil. However, looking at the hat from behind, the foiled side is in fact slightly colder, while the triple layer is as warm as ever. You can see that peeling off the first of the 3 layers of fabric reveals again that the lower ones are not effectively transferring their heat to that cold outer surface. The foiled side, on the other hand, is now much warmer on the outer surface, showing that heat is effectively flowing into it from the back, and this is a good sign. Now, in case we might wonder if the foil alone is responsible for increased cooling, I did separate tests with a piece of foil on the outer surface of a wooden board. In the middle of this foil, I have a piece of cooling fabric cemented to it. Taking a thermal reading from the back of the board reveals that the foil alone does reduce the temperature some, but it's still well above air temp in sunlight, with a definite cold spot in the center where the fabric is located on the outer surface. So the fabric is definitely better than using foil alone. Now, as we look at the hat brim, the foiled section is still well above air temp as measured from the back. And that temperature increase can now also be seen on the fabric itself because heat is more effectively conducting into it from the foil. Aluminum foil still absorbs nearly 15% of sunlight, which is probably much less than polar bear skin, but apparently that's still enough to overwhelm the cooling power of the fabric, causing the overall temperature to rise. So the result of using foil as a fabric backing on my hat is definitely better than relying on multiple disconnected layers, but it's obviously not good enough. If foil absorbs 15% of sunlight, that's 150 watts of heat per square meter that the cooling fabric needs to counteract just to keep it at air temperature, let alone to cool the foil to sub-ambient temperatures. To make this work, I think we need at least one of 3 possible solutions: a more reflective backing for the fabric, a fabric with increased opacity so that a backing becomes unnecessary, or 3, the cooling power of the fabric itself needs to be increased so that it can compensate for excess light absorption. I think the last 2 options might be possible to accomplish at the same time with the addition of pigment to the plastic mixture, but we'll have to try that at a later time. One application which could make very good use of this fabric without any changes is air cooling. If a thin layer of this can reach sub-ambient temperatures even in open air with a breeze blowing over it, then that same layer, if contained in a box with air blowing through it, should be able to cool the air by the time it reaches the other side. Also, a lot of you have been asking me about thermal camouflage for some reason. I'm not sure exactly what the motive is behind that question, but this might do it. The outer surface does stay pretty dark on the thermal cam even when the inner layers are warm. Speaking of which, my focus in this series has been on cooling because I think that's typically the more difficult problem than figuring out how to keep things warm. But did we possibly just discover a new option for making high-performance winter clothing? If this fabric were intentionally layered on top of something dark, we might be able to absorb solar heat near the skin, while the outside layer insulated that heat from the wind. I wonder how effective a synthetic polar bear effect could be. Yeah, we might need to test that. Anyways, for now we've effectively taken the concepts of PLA fiber production from previous experiments and turned them into actual fabric, which demonstrates radiative sky cooling properties for at least some circumstances, with a lot of room for improvement. Remember, we're just working from what I can pull off in my backyard workshop, so keep that in mind if you think this is slow progress. This series is steadily moving forward, and if you're interested to contribute toward my efforts and occasionally catch a behind-the-scenes live stream, you can do so through Patreon. If you don't have the extra income for that, don't worry about it. I love just having you here, and I don't want anyone throwing money at these projects that can't afford it. By the way, the live streams that I've been filming for patrons become public on my second channel once the projects they reference have been completed. There's currently 2 new live streams on the channel Nighthawk and Light Extra, where you can watch me build my fiber-blowing machine if you're interested to learn how that was done. Watching the streams live is a small benefit for patrons, but the recordings eventually go public so everyone can stop by and learn from my many mistakes. Thank you everyone for watching. I'm excited to see where this takes us. I'll see you next time.